Good evening, everyone. How are you all? I hope every one of you is absolutely amazing. This is your chemistry expert Sanjay Arya sir, and today we'll deal with a very important topic from inorganic chemistry named as coordination compound. Probably our final topic, probably the last topic of inorganic chemistry, and right after that we'll start our organic chemistry, and we'll finish our syllabus on time before your JEE Main first attempt, which is going to start from end of the January. So this is what our target for the day is. This is a 12th grade chapter in organic chemistry. We'll start with some JEE Main and advanced PYQs, and also we'll cover the entire important topics of this chapter. So the very first thing that comes in our mind after listening that what are salts? Okay, the coordination compound itself are the salts, a category of salt that is. Okay, finally. Well, thank you, Asim Datta, for this clarification. I hope now my voice is pretty much audible to every one of you. Thank you for being so patient, and thank you, Sachin sir, for your beloved help here. So, guys, I was discussing about the salts. Salts are nothing but the ionic compound formed as a result of acid-base neutralization reaction. The salts can be classified four categories broadly. One of them is simple salt, mixed salt, double, and complex salt. So today we'll be dealing with very important category of the salt, that is none other than complex salt. Complex salts are the compounds that do not furnish all the ions involved in it, and they retain their identity. Anyways, we'll come to it. First of all, let me explain what these salts are. Number one is called as simple salt. The number one salt is a simple salt. A simple salt is a salt that furnishes only one kind of ion while undergoing dissolution or ionization, or we can simply say that these are formed of a single type of cation and anion. So there will be one type of cation, one type of anion, and not more than one type of ion will exist. The examples are pretty cool. None other than the common salt NaCl, Al2SO4 whole thrice, etc. Whatever the salt you can see, there are like one kind of ion only, one cation, one kind of anion. We can easily see. Number two type of category among the salt is called as mixed salt. As the name itself suggests, that there will be more than one type of ions, either cation or anion or both. So they contain, or they are formed of more than one kind of or one type of cation, anion, or both. So very simple example could be, like, in order to explain this part, we can take any kind of example like NH4HSO4. So what can you see over here? Ammonium is one cation, H positive is one cation, and sulfate ion is here. Another could be CaOCl2, we call it as bleaching powder, calcium oxychloride, where two type of ions can be seen. Here we know that two type of cations are present, NH4 plus and H plus. Here two type of anion can be seen. One of them is Cl minus, the another one could be OCl minus, oxychloride anion, right? We call them hypochlorite ion. Okay. I think this is pretty much clear to all of us. Now I'll take you to the another category of salt, and that category of salt is called as double salt. Simply, as the name suggests, double salts are made up of two type of simple salts which are packed in a single lattice with some water of crystallization. So double salts are actually formed of two simple salts joined with some water of crystallization. So there you will find some water of crystallization also. Take this example. The one example could be potash alum. Yes, K2SO4 dot Al2SO4 dot 24H2O. So what is this compound? This is called as potash alum. Actually, what alum? Another example could be more salt. Yeah, I remember more salt. More salt is actually iron sulfate dot ammonium sulfate dot 6H2O. Guys, these number of water which are present in this entire molecular formula, in this entire formula unit, is called as the water of crystallization, and this is the number of water molecules which are entrapped in the lattice that is formed by the potassium sulfate and aluminum sulfate. There's a common lattice there. That is what the type of salts are. Now we have come to the final part of this game, and that is our complex salt. So there is no direct as such definition of complex salt, but we can define them like these are the salts which do not reveal the identity of all the ions present in it. of all the ions oblique molecules present in it. Okay, now let me take you to one of the example and then you will understand it better. Take this example, we call it potassium ferrocyanide FeCN6. Now take this example and try to understand that how many number of ion does it contain? K4 Fe2 plus Cn minus, right? But in aqueous solution, when you basically dissolve this compound in aqueous solution, the number of ion it will show is two type of ion will be there. One is the potassium, 4 K positive ions will be there, and this is in aqueous. The another will be iron cyanide, and this is a complex ion. So this kind of ion, where am I writing it into this square bracket? This species, this something which is written in this square bracket is called as a complex ion. And why am I calling it a complex ion? Because it doesn't reveal the identity of the individual ion it is made up of. It doesn't show you the property of Fe2 plus. It doesn't show you the property of cyanide, but yes, it will be showing you the property of K positive. So such type of salt that do not reveal their properties of all the ions involved in it are called as complex. And these complex salt or the complex ions are represented in this square bracket like this. Now you tell me if any doubt is there. Do let me know. I'll explain you. I hope this part is pretty much clear to all of us. So now up to this complex compound, I will explain you what are those particular terms that we very frequently use. And these are the terms. I would like to first suggest you people to go through these all terms so that I can explain each and every term again. Sir, is mixed salt and double salt are the same? No, beta, no. Absolutely no. As we all can see that mixed salts are the one in which more than one ion is present inside one crystal lattice. But in double salt, two or more type of simple salts are joined together with some water of crystallization. So these two are different kind of compounds. Two different formula unit or two different simple salts are connected there by water of crystallization. That is what double salt is. And in mixed salt, there is only a single lattice is there where there could be more than one type of cation and anion. Actually, there is no, like we can say, a very characteristic difference between even every one of them, because salts are simple salts only. These are the ionic compound that contain cation and anion. The only category which is entirely different from the rest of others is complex salt, because complex salt is the one that doesn't give you the identity or the what we can say, the confirmation of all the ions present in it, because there is a complex ion involved in it, which is a kind of like a species in which central ion is connected with the other molecules or ions via coordinate bond. So that is something that will come to it. Let us first go through each and every term that is involved in coordination compound. The number one is called as coordination entity, the coordination sphere. Now let us take one example right now over here. The same example I'll take, K4Fe CN6. So guys, what you can see from here, I'll explain every single part. Coordination entity, the one which is written down in the bracket, this part is called as coordination entity or coordination sphere. This is called as coordination entity or coordination sphere. Then we have another term called as central atom or ion. Central atom or ion is a particular metal atom, or sometimes it is cation ion also, which is accepting the electron pair by other molecules or ions. Over here, Fe3 positive, sorry, Fe2 positive over here is your central atom oblique ion. So let me write it, central atom. And the ions which are donating which are donating the lone pair in the vacant orbitals of iron. These are called as, the 6Cn minus ions will be called as ligands. Similarly, another thing is oxidation number. So guys, oxidation number is some concept that we have already covered in the previous classes, such as your redox reactions. Okay, I hope now I'm pretty much audible and everybody can listen me. Yes. The next is oxidation number. Oxidation number is something that we can find out using the same mathematical formula we used to study. So how can we find it? Potassium usually in its compound is always present in positive 1 oxidation state. So 4 times of plus 1 oxidation state plus iron, we have to find out the oxidation state for the central atom of the complex species, plus 6 times of minus 1 charge is present on every cyanide atom. Overall charge on the molecule is 0. That gives you X is equals to 7 minus 4, uh, 7 minus, not 7, 6 minus 4 is equals to positive 2. So this positive 2 is called as the oxidation state of central atom. Another term I can see is coordination compound, coordination number. Coordination number is the number of covalent bonds or the coordination bond which are formed by the central atom with other ligands, and I can see the number over here is a 6 because Fe is connected with 6 cyanide atoms forming 6 coordinate bonds. Hopefully this part is pretty much clear to all of us, and even if it is not, do let me know in the comment section. The comment section is highly open for all of us. Do let me know and I'll resolve your doubt immediately. Moving forward, we have some of the very important coordination numbers that are used in the formation of compounds. These metal atoms or ions which you can see are the one which form the majority of complex compound. And what kind of coordination number do they possess while having that particular oxidation state is written over here. We got to take an idea. We are not supposed to rote learn the entire table. We just need to take the idea. Take the idea like copper, whenever it is present in positive 1 oxidation state, shows two type of coordination number. Either it can form you CuCl2 positive type of compound, or it can form CuNH3 whole 4 positive kind of compound, where copper itself is present in the oxidation state of positive 1, and coordination number could be 2 and 4. So very important part to learn about. Then we have silver. Silver in Ag positive generally has a linear molecules, and it will give you coordination number 2. Au has 2 and 6, 2 and 4. Copper 2 plus has 4 and 6. Pt2 plus is 4, 4, 6. Nickel 2 positive will show you 4 and 6. We'll come to it later on. Iron also gives you 6. Iron 3 plus also 6. Cobalt in positive 2 gives you 4 and 6. But in 3 plus, majorly it gives you octahedral geometry. Octahedral geometry with 6 coordination number. Platinum also has 4 plus, and Pd4 plus also has the 6 coordination number. This number is something that we need to take the idea about. We are not supposed to rote learn anything down. Okay, mistakenly came here. Then we will be starting it with the basic term called as type of complexes. So depending upon how many number of ligands are there inside a particular complex, there could be broadly two type of complexes. One of them is called as homoleptic. Homoleptic means only one kind of, right? Homoleptic are one where only one type of ligand, only one type of ligand is present. Where only one type of ligand is present, such kind of complexes are called as homoleptic complexes. Take this example. So let us take this example, cobalt with hexa ammonia molecules and Cl3. So how many number of ligands are there? Yeah, ligands could be 6 over here, but type of ligand is only one. One kind of ligand is there, which is ammonia, right? Sumesh is saying that thermodynamics notes are uploaded. Don't worry, buddy, don't worry. I will upload them. Telegram channel link is given in the description itself. Go and follow our Telegram channel, and I will re-upload these notes by the end of the day. My promise. Don't worry. Now let us focus on this. We were here discussing that heteroleptic are complexes where more than one type of ligand is present. Those complexes where more than one type of ligand is present are called as heteroleptic complexes. And the example could be anything that we can take, like PtCl2 NH3 whole twice. So this compound could be the one. Why is it heteroleptic? Because it contains more than one type of ligand. One of them is chloride ion, another one is ammonia ion. Anyway, ammonia molecule. I'll let you know about type of ligands also very soon. So this is the basic introduction part of this chapter. Now I think we should start solving one question, which is very easy question, but this has been asked back in 2019 JEE Main. A question was asked in 2019 JEE Main about which of the following is a heteroleptic or homoleptic complex, like that. So try solving this question. Which of the following is a homoleptic? Now homoleptic, we all know about homoleptic. They contain only one type of ligand. Now you can give me the answer. Okay, thermodynamics was already given to you. Thermochemistry was not given. I got your point. Thank you, Sumesh, for your feedback. I'll submit those notes and I'll re-upload those notes. Okay, don't worry. Try solving this question. I think this is hetero, this is homo. This is again hetero and hetero. B is the correct answer. Next question. We have been given with a molecule here. A complex compound is given to us. It's a complex ion, by the way, and we got to find out the oxidation state of the central ion here, which is nickel. So guys, let us consider the oxidation state as X plus how many molecules can we see? 5 times of 0 charge plus 1 times of -1 is equals to overall charge is +1. So X will become up as +2. Nickel in this complex is present in +2 oxidation state. How easily we can find out? So this concept is pretty much clear to all of us, and this is very much related with the redox reactions that we have already covered. Then we have classification of ligand. So guys, classification of ligand can be explained based upon so many things, but broadly we'll go for the denticity, right? So let us say if we talk about the number of coordinate bonds, formed by one ligand molecule or ion at a time is called as its denticity. What do we call it? Denticity. So denticity means how many number of coordinate bond a single ligand can make at a time with central atom. So depending upon that, we will classify the ligand based upon its denticity. So now you can check. There could be multiple denticity like monodentate, bidentate, tridentate, tetradentate, penta, hexa. Hexa is huge and we do not go generally beyond that. So this is what we have to consider it about till hexadentate. We are starting it from the monodentate. Monodentate, all the anions that you usually see, which are usually containing one negative charge or sometimes one lone pair above them, or sometimes even more, but can form only one bond usually, like halide ions, like oxide ion, like hydroxide ion, like nitrate ion, sulfate ion. All those ions which can only form one coordinate bond with the central atom are considered as the monodentate ligand. So these are the pretty much examples, as you can see, and these examples are highly sufficient. These examples what we need to basically consider, and I think I have covered enough of the number of ligands here. So just take the idea and let's move forward. Okay. Then we have Bidentate, very easy example could be bidentate means where you can release two electron pairs or two lone pairs can be lost by one ligand at a time. So let us suppose this is a metal, and ethylene diamine is very good example. Ethylene ethylene diamine ethylene diamine. So what is ethylene diamine? This is a group CH2 NH2, sorry, CH2 CH2 NH2 NH2. So guys, as we can see that this is the central atom and this is how it can form two coordinate bond at one time. Also it is forming a cyclic ring. So such type of ligands are also called as chelate ligand because we call the circular ring as chelate, and this process is called as chelation, but we'll understand this concept of chelation later on. Right now, very important part is that ethylene diamine can form two covalent bond at one time, and that's what is considered as the bidentate ligand. The another such example could be this called as 110 phenanthrolene. Phenanthrolene, we write it like ophen. Ophen is the symbolized, ophen is the symbol of this ligand. Then we have salicylato. Salicylato, SAC. SAC is the representation. Salicylato is the anion that is formed by salicylic acid. We usually study this compound in Kolb's reaction, very important reaction in the organic chemistry. All clear? No problems as such? Very good. I'm continuously monitoring the uh, chats also. So if anyone faces any doubt, do let me know. And if I do not reply on any kind of your chat, that means like I'm continuously monitoring it, but whenever it will be needed, I'll give you the answer. Okay. Till here, we all are on the same page. Everything is going very fine. We all know what we are studying and we all have cleared this part. Another examples are also there of bidentate. As I told you that I have come up with all the important ligands that are actually existing. So guys, my notes are highly enough for your JEE Main and advanced preparation. What you can do from your end is just download the notes, try to make out the short notes out of my complete notes so that you can easily quickly revise the particular chapter in just one go. Okay, only make a one page notes only, and that will help you. And try solving the solved questions given inside this complete notes, and then right after that you can apply some PYQs, and that will be highly helpful for your JEE Main journey that you are going to face very soon. So now we have another some example is called as ACAC, which is acetyl acetonato. And I'm okay. The structure and the name, everything is given over here. I will not rush it out. I will not just okay rewrite everything. So this is it will save our time also, and it will save the my proper handwriting also. So 2,2-dipyridyl is dipyridine, which can donate from these two lone pairs. So this is also dipyridine. Then carbonate ion. Carbonate ion has two oxygen atom with two lone pairs to donate. Then we have also that glycinato. This compound is called as glycinato and we represent it by gly. The symbol is gly. So glycine is one of the amino acid. See, look at this. This carbon has two hydrogen, one COOH group, another NH2 group. If you remove one of the H from here, it will become O minus. O minus can also donate. Nitrogen can also donate. It's a bidentate ligand now. It's a bidentate ligand now. There we have tridentate. The very common example is diethylene triamine. That means CH2 group which is connected with NH here, another CH2 group, and then it is connected with NH2. Here also CH2 is here. It will come up with NH2. So guys, as you all can see, one donor atom, the another donor atom, and there is a third donor atom, and these all are connected with the methylene group. No, we call them ethylene group. So the name of this compound will become diethylene triamine. Diethylene triamine. Representation is diene whenever the naming is there, or whenever there is a short abbreviations used in order to determine, in order to write down this particular ligand, we use diene. There are also some more important tridentate ligand. As I told you, I have come up with all the possible ligands here. It is called as 2,2 terpyridine. It's nothing but just three pyridine rings are here, and three pyridine rings can donate three lone pair called as tridentate. The another example is this nitrile triacetato. Okay, nitrile triacetato is nothing but the nitrogen atom connected with CH2CO, CH2CO, CH2CO. All three can donate at one time, and this is a tridentate. Next is tetradentate. Tetradentate, you can also make it by your own. That NH3, NH2 is the group that can donate and connected with the ethylene group. Then another NH group is here, which will be connected to another CH2, CH2, one more NH, and then CH2, CH2, and then at last we have NH2. So guys, how many number of nitrogen can you see which can easily donate the electron pair? 4, and that's why this is called as a tetradentate ligand. So you can also form this molecule by your own, no requirement of rote learning it. It's called as how many ethylene group are there? 1, 2, 3. So it's triethylene, and how many amines? Tetra. So it's triethylene tetraamine. In case of any confusion oblique doubt, do let me know. I'll help you. I will continuously monitor the chats, but I will not let you know. Sir, why did Akash sir not taking the classes? Akash sir actually are in some family emergency, and due to which he is not taking the lectures as of now, but don't worry, he will come and join us very soon. Okay. Next. Next is pentadentate, and one example could be like ethylene diamine triacid. What is it? EDTA 3 minus. Okay. So this compound is very much important, everyone. EDTA 4 minus and EDTA 3 minus are two very important examples. Ethylene diamine tetraacetate. Okay, let me show you the structure. Ethylene group is CH2, 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 CH2. Then amine is there. How many am I supposed to make? 5 pentadentate. See, 1, 2, 3. No, it's too much. The structure is not good. Actually, I remember this question was also asked in back in 2010 JEE IIT JEE exam, and the structure is somehow look like this. So I actually forgot it for a while, but now I have recollected the information, and now I can draw its correct structure. CH2CO, which is called as the acetate group. CH2CO. So how many acetate groups are there? 4. No, it's 3. So how much is the denticity? We can check it out. 1, 2, 3, 4, 5. It's a pentadentate structure. The another example could be hexadentate, and this is EDTA 4 minus. See, the representation might be exactly similar, but the charge over here is 4 minus. Earlier it was 3 minus, now it is 4 minus. How does the structure look like? It is ethylene. Ethylene group looks like this. Diamine means 2 nitrogen atom have to be set here. Ethylene diamine tetraacetate. Tetra means 4 acetate group will be here. So acid group is CH2CO minus, CH2CO minus, CH2CO minus, and then we have CH2CO minus. This is called as EDTA 4 minus. That was it. That was the classification of ligand. You all came across. Now we have EDTA 3 minus is a type. Oh, we all know it's penta. Man, EDTA is a very popular example. 4 minus is actually hexa. Next is some of the classifications are based rather than density. We'll discuss about their other properties, such as one of them is called as flexidentate. What is the meaning of flexi? Flexi means wherever it is required, they will give you the requirement. Like EDTA 4 minus, it might be a hexadated ligand, but wherever it is requirement, there is a requirement of just 4 ligands only, or 4 coordinate bonds with the central atom, EDTA 4 minus will form only 4 coordinate bond. That's why we consider EDTA 4 minus as a flexidated ligand. Take this example. Take this example, sulfate. Sulfate ion has 2 donor side, 2 oxygen atom, but every time it doesn't happen that both of the oxide ions are donating it. Sometimes wherever it's a requirement of only one lone pair to complete that particular complex compound, then only one oxygen atom will be donating this and another will be having its negative charge with it. Take this example. This is working over here as a monodentate, as you can see, and this works as a bidentate. No problem till here? Not at all. We have another example of such category, that is nitrate, acetate, and thiosulfate here, that may also act as flexidentate. Carbonate ion also can form as monodentate and bidentate in some cases. Here carbonate ion is working as a bidentate, right? Here it is working as a monodentate. See, then we have, apart from flexi, we have ambidentate. What is the meaning of ambidentate? Ambidentate ligands are those which can form which can form only one or two, like whatever it is decided. They cannot change the number of density, but their donor atom can be changed at once when they are making the bond with the central atom. Just take this example of cyanide and isocyanide. Cyanide ion can form a direct bond with the metal atom, with carbon atom. Cyanide, the carbon atom of cyanide can form the bond, and it is called as cyanide. It can also be called as isocyanide if nitrogen forms a direct bond with the central atom. So this depends which of the connecting atom is connecting with the central atom. So these are called as the flexidentate. Take these examples: cyanide, isocyanide. This is called as cyanato, isocyanato, or we can also call that cyanato O, cyanato N. This is called as thiocyanide S, thiocyanide N. This is called as nitroso N, nitroso O. This is called as carbonyl C, carbonyl O. This is called as nitro N, nitro O. This is called as sulfate. What is it, by the way? Thiosulfato, no? Thiosulfato S, thiosulfato O. Like that. Take my words in account. Try, make your short notes. Hear me what did I just say, and make your notes and just try to learn these compounds. These are highly important. Now, ambidentate ligand, continuing it, the ambidentate ligand, it's not required that somebody which is having some ligand which is having a monodentate can only be ambidentate. No, even a ligand like this can donate through oxygen and can sulfur. These two are also ambidentate in nature. These two are at the same time bidentate and ambidentate to each other. Take this example. So which of the following ligands is both bidentate and ambidentate? As we just came across, this is the compound where the carbon are connected. Wait, let me check. This is how it do. Double bond S, O minus is a donor atom. O minus is a donor atom. The another structure can be represented as now check out the donor atom. Now, chelating ligand, guys, chelation, I told you once earlier about it. Chelation, we can call it just chelation. So just chill, dude. Chelating ligand are those kind of ligand which form a cyclic, or we can call it a ring type of structure, because No doubt, chelating ligands are always polydentate in nature, because if they can form only one monodentate ligand, if we have as a one monodentate we have ligand, they will never be able to form the cyclic ring with the complex ion, where the central atom should also be a part of the complex, that particular ring which we are talking about. So chelating ligand is the one that can form a ring structure with the central metal atom, and polydentate ligands are the example of chelating. One of the very good example is your EDTA, ethylene diamine tetraacetate, is also one of the good example of poly, sorry, chelating. Okay, and I'll show you one more example, that is nickel and En whole twice 2 plus. Take this example. So what is happening in this example? Nickel is present in positive 2 oxidation state and will be forming dative bonds in two sides of nitrogen. Similarly, another such molecule is there. Check it out. It's a cyclic ring structure. These are the examples. Now try this question. This question is saying that which of the following ligand is not a chelating agent? Chelating agent is the one that is a monodentate in nature. So it's a hexadentate. Ethylene diamine is bidentate and it can also form a ring. Oxalate is also bidentate and can form ring. But pyridine is the one that only forms on one bond at one time. This is how the structure of pyridine look like. So this cannot form a chelate. Although this is a cyclic ring, but after donating the lone pair, after forming the coordinate bond with the central atom, the central atom should also be a part of the ring, which it is not. You can check it out. The ring is also have a member of nickel. 1, 2, 3, 4, 5. It's a penta membered ring. 5-membered ring. Next question. If a monodentate ligand can ligate through different atoms, we call them no flexi, chelating no, no, ambidentate is fine. C is the correct answer. C is the perfect answer. There was a question that was asked back in IIT JEE 2010. This question was asked back in IIT JEE 2010. As I told you, I appeared in this examination. I remember this question came in my exam. So the structure was only asked. I don't think that's a tough question. It's very easy question to solve it with. Ethylene group is CH2CH2 connected with 2 nitrogen atom and then CH2COH, CH2COH. C. C is the perfect answer. So no need of getting confused here. Most easy question of the day. Then there is one more question that was asked back in 2013. Okay, 2013. That EDT4 minus is this the total number of NCO bond angles in the complex ion. So what you think? Tell me. Something that need to be discussed here. Let us suppose this is cobalt 3 plus and the molecule is N ethylene diamine. So let us say CH2 I'm putting here. Nitrogen will form one bond here. Then we have CH2CO minus, CH2CO minus. In the similar way, here also nitrogen is here. CH2CO minus, CO minus. How many bonds can we form by the way? See, 1, 2, 3. 1, 2, 3. what we have to do is we need to give it how many number of NCOO bond angle, NCOO. So NCOO 1, then NCOO 2, then one N of this, another CO of this. Okay, I can see it now. So one nitrogen, one nitrogen is connected with 2 CO minus, 2 C is to CO minus, and number of NCO. See, this is also one of the bond. Nitrogen, cobalt, and oxygen. This is also one of the bond, one of the bond angle. So one nitrogen is actually forming, I can see, one nitrogen is actually forming 4 NCO bond angle. So how many nitrogen are there? 2 nitrogen will form how many? 8 is the correct answer. Maybe I was not appeared in this exam of JEE 2013, but yes, this seems an easy question to me. You can check out the answer. I know there are some set of some good presentation of this molecule also, but I don't believe in that particular presentation. I believe that I can draw however I want and I can get through the answer. So this is pretty much clear to all of us. The number of bond angle was asked to us. We already have finished it. Now we'll move forward with the IUPAC naming of the complexes. So IUPAC naming of the complexes requires some set of rules. For an example, it's a compound. So here is a compound. Let's suppose the compound is K4. Okay, no, this is a cobalt NH3 whole 6 Cl3. Another compound is FeCN K4 or K3, no, K4 FeCN6 is fine. Now I'll write the IUPAC name of these two compounds and then I will explain what kind of rules have been followed while writing the IUPAC name of complex compound. Taking this compound in the account, complex compound cobalt has the oxidation state x plus 6 times of 0, 3 times of minus 1 is equals to 0, x comes up as positive 3. So the name of this compound will become what? First we are supposed to take the name of cation, then anion. Like sodium chloride, in the similar way, this compound cation then followed by anion. So this is hexaamine. We are supposed to write down the ligand's name first. Then we have cobalt. Then we are supposed to write down the oxidation state of cobalt in Roman numeral. And then we have chlorine. So we are not supposed to write the trichloride. We can simply write chloride. This is the name of this compound. Let us talk about the name of the another complex molecule. Let's see if it works. So this is your 4 times of positive 1 oxidation state plus x plus 6 times of minus 1 is equals to 0. X comes up as positive 2. So what I can do is potassium, first cation then anion. Potassium is, we are not supposed to write it tetra potassium. This is obvious that 4 potassium ion will be used here because the complex ion itself has a 4 minus charge. Potassium, and then how many number of cyanide there? 6. So hexa cyanido or cyano also we can write. Then we have iron. So instead of iron, we'll write it ferrate because this is a part of anion. Whenever anion is complex there, then the central atom becomes ferrate. Ferrate with its oxidation state positive 2. That is how we named it. So I have already named these two compounds, but still we need to understand how did I do it, what kind of rules did I use, how can we use these compounds to name them very easily. So this is the part that we have to cover. First of all, we'll start learning the name of ligands. So guys, ligands which are cationic in basically charge, they are named with ending with ium, like nitrocilium, hydrazinium. Okay, nitrosyl is the compound and nitrocilium, ium is something that is added. Okay, Then the neutral species are named with their special name, like water is written down as aqua. So, guys, notes are highly enough, as I told you. Even if you go through the notes, you can easily reach to your required milestone. But just take this idea and study it in the better way. Hello, hello, yeah. So, we'll continue this part. These are the names of neutral ligand that we have to learn. This everything is given over here. You can go through each and every molecule. Just like carbon monoxide as a ligand is known as carbonyl, nitrosyl, then acetamide, methenamine, right? These are the common names. Benzene. Now, if there is anionic ligand given in the complex, then anionic ligand is written down with its name and it ends with O, like chlorido, fluorido, bromido, sulfato, carbonato, oxalato. O will be added in the name of these complexes, right? Like this. Then what happens with ambidentate ligands? So, guys, what do we do? Like, take this example. If this is cyanide and this is connected with carbon, so we can say that this is called as cyano C, or it also becomes, if it is Nc minus with negative with this low donor atom as nitrogen, then it becomes cyano N. So that is the method where we can use it. Take another example. Let's say nitrogen in this nitrate ion. In this nitrate ion, nitrogen is the donor atom, so it is written as nitro O. And the another example could be, let's say donor atom is nitrogen itself, then it will become nitro N. So this is how we do. So it's very simple. We can identify which is the donor atom, and then we can put down the name of the donor atom as its chemical symbol. Then comes naming of mononuclear coordination compound. Mononuclear coordination compound means the cation is named first in both positive negatively charged entities. So how are we going to name this thing? As I told you, we gonna name cationic part first. So it is potassium. This becomes hexa, cyano, ferrate, and then its oxidation state is 2. Talking about this is, now we have two type of ligands in it. One of them is ammonia, another one is Cl. We need to take that one first, which has the alphabetically higher priority. Alphabetically comes first, which is amine. So how many amines are there? We will write the name as penta amine. AMMINE is the special name of ammonia molecule, which is right, just like aqua we used to take in the neutral molecules of ligand. Pentaamine, then one is chloride, then we'll simply write chloro, then is cobalt. So what is the oxidation state? Usually it is positive 3 in the cobalt complexes and especially in the octahedral complexes, and then comes with the end of this chloride. That is how we write the name. So what you need to follow is just follow the rules which are given over here and move to the another rules, and then you can write down the name of anything whatever you want. So the name of the ligand which is listed before the name of the central atom in an alphabetical order, it will come. The meaning of this thing is, here what we see, one of them is ammonia, bromine, chlorine, and then we have En. En is ethylenediamine. So which of them should be named first? No, methylamine is the name. So undoubtedly amine will come. So I'll write this compound as amine. Then we have one bromo, chloro, methylamine, and then it ends with platinum. What is the charge here? Okay, neutral. Platinum with its oxidation state as 0. No. Positive 2 is the oxidation state. This is how we can do. And now you will try the same by your own. So whenever there is more than one ligand present, the alphabetical order will be followed. Next is prefixes like di, tri, etc. are used in order to indicate the number of one kind of ligand and in the coordination entity. When the name of ligand is already included, the numerical becomes bis, tris, tetra, case like that. So guys, try to understand what is this rule mean. So let me take this example here. Take this example. What we can see, there are two type of ligand. One of them is chloro, another one is triphenylphosphine. But triphenylphosphine is both of them are in like 2 in number. Like this is also di, this is also di. We are not supposed to write di 2 times. So one time we'll write it di, another time we'll write it bis. So I'll write the name as, see, dichlorido or dichloro. Then I will not write the di, I will simply write bis. What is bis? Bis triphenyl phosphine, then nickel. And since this compound is a neutral compound, I am not supposed to write it as nickelate, simply write nickel. And nickel with its oxidation state, usually it is positive 2, and you can also check it out. You can even find out using the formula that x plus minus 2 plus 2 times of 0 is equals to 0. X comes up as positive 2. Now read out these two rules. One of them is you will put 8 whenever this is present in an ion. I have already told you this rule. The another one is the oxidation state of central should be written in parentheses. I have already covered this part. I will move to the next one. Now one of the example is given to us. I'll give you one example, then we'll come to the questions solving these part, and then that is how it ends. So platinum is there, and so many things are there. First, you need to find identify the oxidation state. X plus this is 0 plus -1 plus -1 plus nitrate is also -1 is equals to 0. So X comes up as positive. Are we sure? Okay, okay, okay. It is not equals to 0. It is equals to -1. So this comes to as positive 2. Now you have identified the oxidation state. Try writing the name. Ammonia, amine will come first. So it's simply amine. Bromo, chloro, which comes first? Bromo, chloro, nitro, N. It's NO2. I'm writing nitro N. Whenever it is written as ONO, we'll write nitro O. And then it's an anion. So we'll write, instead of writing platinum, I'll write it platinate. And what is the oxidation state of platinum? Positive 2. See how easy is this? How easy is this part? That's how we name these complexes. Another example that I think you better try the examples by your own. And even if you want, I can give you this answer, but later on you must try the examples by your own only. And in JEE Main point of view or JEE Advanced point of view, I have seen some of the questions which are directly asked for the naming of these compounds. So my suggestion is better go for naming. Try solving more and more questions on this topic. Very useful topic. So this will become what? X plus -2 plus 0 is equals to 0. So X will become what? Positive 2. Now writing the name, how are we supposed to write down the name of this compound? Dichloro bis. What is this compound? Methylamine. Bis methylamine. Then copper, and oxidation state is positive. See how easy is this? Now try this question. The name of this molecule is very easy. So first we'll write aqua versus amine. Amine will come because aqua contains AQ and it contains AM. AM will come first. So try amine, di-aqua, 1 chloro. Okay, so chloro, cobalt 3 chloride. I think B is the correct answer. You can solve these questions like this. Have that confidence. Another question, the IUPAC name of this compound is. You try this question. I'll be back and joining you soon. Try this question, everyone. Please try. So hopefully you people have covered this part. Maybe this question has been solved. Yeah. So we got to give the name of this compound, and such kind of compound where both of the cation and anion are complexes, we got to follow both the rules that we were earlier using it for cation and anionic part. Starting from this, mainly you will find that these kind of compound have common oxidation state of the central atom. If not, it will be given to you. You can easily find it out. One more point I want to mention here is, as we all remember, the most common oxidation state of the complexes, that also gives you an idea what kind of oxidation state has to be used. The another example could be, like consider both of them are in the same oxidation state. You may write it like 2 times of X plus how many ammonia molecule, 6 with 0 charge, 6 cyanide with -1 charge, overall neutral, X comes up as positive 3. Now oxidation state of both of the central atom is known to us. Now what we'll do, we'll try writing the name of this, starting from the cation and then we'll come to the anion. Hexa amine cobalt 3 hexa cyano chromium, not chromium, it will become chromate because it's a part of an ion now. Chromate with its oxidation state 3. That's how we do. Very simple, very easy. Anybody can do it. Now this example, you will do this example by your own. Now I'll tell you how can we name the bridging complexes. What are the bridging complexes? Let us first know about bridging complexes. There could be a bridged ligand. What is this bridged ligand? This is the bridged ligand. A ligand that is present between two central atoms. So this ligand could be polyatomic or it could be monoatomic also. And ligands which are not bridging are normally called as terminal ligands. Take these examples, everyone, and try learning the name of each and every bridging ligand, because that is what very much helpful in order to knowing the IUPAC name of such compounds. Just remember and just try to once learn all the names mentioned here. Hydroxide, oxides, hydrosulfide, amido. Okay, NH2 is amido, nitride, carbonyl, chloride, hydride, cyanide, diphenyl phosphide, alkoxide, alkylamide, amido, phosphido. Good. So there could be 3 ways to write down the name of a bridging complex. Very one, if a bridging complex is symmetric around the bridge, so this is your bridge, oxido, simply oxide, sorry. We write them normally oxo, we write them oxo. both of the side, either of the side, if the same kind of compound, same kind of species are given, these kind of complexes are called as symmetric complexes. Symmetric Bridget complexes can be termed as, they can be named into three ways. One of them is this. Simply you need to write mu oxo and then bis. Bis means like doubling the side-wise entity, that is chromium with 5 amine. So pentaamine dichromium, sorry, pentamine chromium and this ion. This is the one way. Check out the another way. Pentaamine chromium. Okay, now what we'll do, we'll start it from the left and we'll go towards the right. Whatever it comes in between, we'll try to name them. Pentamine chromium third, mu oxo pentamine dichromium 3 ion. This is another way. Third example, third way could be, we are just simply considering the whole molecule as one unit and we'll write mu oxo. This is the ligand bridging mu oxo. Then how many amines are there? Decaamine dichromium ion. Another way. This is another way. Now solve this question. Bridging ligand is given to us. So there could be two ways. One is considering both at once, both of the compartments are symmetric, then it's a counter ion. Both of the ways can be applied. Third one cannot be applied. Third one is this one, mu oxo, then deca. Because we have two basically compounds here, no? Even we can apply that also, like we can write down di mu chloro, and then how many ammonia can you see? Tetra. Tetraamine. Tetraamine diplatinum and oxidation state of platinum, I think it is Cl minus, Cl minus, it is 2, and at end chloride. So these are the three ways in which we can write down the name of any kind of Bridget complexes. Okay, any kind of confusion, do let me know. I'll update you. The most easy way to name is the one that I always prefer, going from left reaching to the right. Simple. I find this the most simple and most adaptive way, but it all depends upon the number of options you've been given with the naming of these compounds. How many ammonia are there? So 4. So we'll write it tetraamine, and then we have cobalt. No doubt it will be present in positive 3 oxidation state only. Then we have 2 bridges here. We will write them as per their preferences of alphabetical order. First comes amido, mu hydroxido, then cobalt. Again, we'll write the same, tetraamine cobalt ion. It's an ion. Now check out the name and then we'll solve some of the problems. We'll practice some of the questions on the same concept. Just try to learn it and then start solving it by your own. There we go. The IUPAC name of the following compound is pentamine, cobalt, NH2 is here. Okay, we can simply go from left to right. Pentamine, cobalt, 3, mu amido, then aqua comes first or what? No. Tetra, amine, aqua, cobalt, 3, chloride. Now check it out. Okay. Oxidation state is fit. Yeah. Check it out, everyone. D is the correct answer. Then we have another similar question. I'll give these questions as homework to you and we'll move forward. Homework, try these questions in homework. Their names are also try this question is in homework. Which type of ligand are mentioned in the bracket? Monatomic or polyatomic? Polyatomic, no doubt polyatomic. If the compound is like this, there is no bracket we are using. If the compound is like this, we have to mention a bracket here. So where are we mentioning the bracket? Where? What is given to us? Polyatomic is given to us. Now another thing comes, how can we derive the molecular formula of a compound from its name? So let's say some name is given to us, like randomly taking some name, dichloro, dichloro, tetra, dibromo, tetra, chloro, cobalt, 3, phosphate. Let us suppose I'm randomly taking this ion. This name is there, it's a complex compound. How should we proceed? You first need to identify the central atom. Write it down, CO. And no doubt it's a part of complex. Okay, first you need to identify cation and anion. This is the cation. Anion is phosphate, so write it down, PO4 3 minus. Till now we are not supposed to write down anything, just write them separately. Cobalt is here, then what we have? Dibromine, so we will simply write it Br2 Cl4. And what else do we have? Nothing else. So cobalt is present in 3 charge, so this is positive 3. These are -1, these are -1. So how much would it become? Total charge 3 plus 6 times of -1 is equals to -3. So this will give you a charge of -3. So cross multiply -3 or just do nothing. This is your entire formula. The final formula of this complex will become CO Br2 Cl4 PO4. That's how we do. Follow these steps and you can write down the formula from the given name of a compound. Now you try this question. So now we are supposed to write down the formula of this compound, dibromido bis ethylenediamine and all. Do one thing, cation anion segregate, Br minus, and here is some complex. Central atom chromium, one of them is bromide, diethylene bis means we are supposed to write it En2. Bis means already we use di, so now we are using bis. Find out the charge. This is positive 3 given to us. This is 0. Oh, sorry, no. This is minus 1 charge. This is 0 charge. So 3 plus 2 times of minus 1. How much does it come? 3 minus 2 plus 1. This is plus 1. The minus 1 just simply cross multiply and you will get your answer. So I think the correct answer is B. This question was asked in JEE Main 2024. Try solving it by your own. Okay. So we all know that this is Br2 bromo and this is triphenyl phosphine. I think we must write bromo first. So we'll write it like di bromo bis. After writing bis, we can use a bracket for this separate kind of complex ligand. This will become trimethyl phosphine. And then I think that's it. Then we have platinum. And oxidation state is positive 2 because bromine is also in -1 oxidation state and it's a neutral compound. Platinum will have a positive 2 oxidation state. Now check out the correct answer. Dibromo and bis trimethyl. This I think C is the correct answer. Yes, C. There is one question that was asked in JEE Advanced 2015. JEE Advanced 2015, this question was asked. In the complex of acetyl bromido dicarbonyl bis tri blah blah blah, number of iron carbon bond. So even basic questions have been asked so many times. This is what I can observe. Basic questions are sometimes asked very frequently. Okay, so what I'll do in order to solve this question, we got to know the formula of this compound. Iron is there, which is bonded with acetyl. Acetyl is, I guess, C double bond or CH2 group. Acetyl. Bromido. Then dicarbonyl. And then bis PPS3. Now tell me, where can you find the carbon iron bond? Simply carbon iron bond. 1, no, 2, 3. 3 are there, I guess. So this is the question, everyone. That is how we get the answer. That's how we do. Okay. Next question is sum of the oxidation state and coordination number of cobalt. So coordination number is pretty much obvious. Bipyridine makes 2 coordination number, 4 is here. So simply I can write down coordination number. Coordination number is 6. Now coming to the oxidation state. So sum of the oxidation state and coordination number is asked. Now we got to calculate out the oxidation state. See, 1 plus x plus 2 times, okay, bipyridine is 0. 4 times of minus 1 is equals to 0. X comes up as positive 3. And we all know cobalt in its positive 3 oxidation state forms the octahedral species. So the correct answer should be 6 plus 3 is equals to 9. These all questions will be done by you as a homework. I can't solve all the questions. We have plenty of things to cover. So this is another homework you will cover by your own. Homework, 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 homework. Then we have another topic of the day. Till now we have finished the classification, the properties, the important terms, and IUPAC nomenclature, and the derivation of formula from the IUPAC nomenclature. This is what we have covered till now for the complex compounds. Next topic, which is another interesting topic, is called as Werner's theory. It's a kind of theory that was proposed by Werner about the complex compounds, and he was the very first scientist who gave the approach of these kind of compound, which are very different from the other salts that we have studied. So let us see what Werner theory has to say. Alfred Werner was the name of this guy. He proposed that he prepared actually and characterized a large number of complexes and studied their physical and chemical behavior and found different physical and chemical properties for complexes even with the same molecular formula. So there he derived that there is a different number of uh, some kind of ions present inside and outside the coordination sphere. So he also gave us the idea of primary and secondary valency. So guys, let us study all of these. In a coordination compound, a metal shows 2 type of valencies. One of them is called as primary valency, another one is called as secondary valency. Primary valency is also called as the oxidation state of this central atom oblique ion. And secondary valency represents the coordination number, which is the number of coordinate bond that is formed by ligands with central atom. Secondary valence is not ionizable. We all know they forms coordinate bond, and that's why they do not get easily dissociated. Only ionic bond can be ionized in water. Primary valence is normally ionizable and they are basically satisfied by the negative charge ion present outside of the sphere. Then we have secondary valency is also equal to the coordination number. So simply learn these two things. Number one of them is called as primary valency. Primary valency of a central atom means we are talking about the oxidation state, and secondary valency is actually the coordination number. That simple. So coordination number, sorry, primary valency is represented by dotted line, secondary valency is dotted by thick line. Negative charge may be often show dual behavior, satisfying both primary and secondary. Okay, I'll represent this compound. Let me just make this compound. Guys, check it out. Cobalt has one chlorine and 5 H2O. So let us say this is cobalt, one chlorine, 5 H2O molecules. So I have marked these straight line with the solid line, and these solid line are representing the secondary valencies of a complex. Secondary valencies are represented here. And let's say secondary valencies are represented by these pink arrows. Then coming to this primary, as we all can see, 2 Cl are outside and 1 Cl is inside. The inside one can represent like this also. This is representing that one of the chlorine atom is acting as both, satisfying both primary as well as secondary valency. Rest two can be represented by us in this way. So this is the concept of primary and secondary valency. This is how it is represented. Cobalt can also be given up as its charge +3. Let us try some questions on this theory. Which of the following complexes will consume more number of equivalents of AgNO3? Guys, this theory is absolutely simple. It's that simple that whatever the compound you can see over here, after ionization, they will produce complex ion that will retain its identity in the aqueous solution. 2 positive plus 2 Cl negative. So how many Cl negative are there? 2 moles. Similarly here you will get 3 moles of now what will happen? Simply as many as number of chloride ions are there, that many number of AgCl will be precipitated out. This is the correct answer. It's very easy concept to apply. Then that was asked back in 2016. In 2016 JEE Main exam, this question was asked. How easy is this question? Another question is here. Okay, I'll solve this question also, but right after it, every question will be solved by your own. You will solve this question. You will solve the followed-up questions. It's a huge chapter. We got to cover so many things from here. That's why I'm asking you that something has to be done by my end, something has to be covered by your end. One of the octahedral complexes is given to us with molecular formula COCl3.NNH3, and upon reaction with excess of AgNO3, it gives you 2 mole of AgCl. That means surely 2 molecules of, it gives you 2 moles of AgCl. That means the compound formula will be CO. 1 Cl is inside. It's an octahedral species, that is why 5 will be here and Cl2. Considering the oxidation state of cobalt as X, so how much is the X? X plus, generally we all know that it shows you +3 oxidation state only, but still I'm calculating it in order to confirm down. X will come up as +3. So we all know X and N. 5 plus 3, 8 is the correct answer. See how easy is this question? Chaliye. Now we have another question, and rest of the question will be done by your end. I'm writing homework. Already answer is given. Homework. Homework. So many questions are there, and then we have come to the next topic. Apart from your Werner theory, next topic comes is Sigwick's Ian rule, effective atomic number. So guys, what is the meaning of effective atomic number? It actually represents the number of electrons that is possessed by the central atom. The central atom contains a set of electrons that is actually contributed by both of the cases. Both of the cases as in, allow me. Both of the cases means, yeah, one is the electron by itself, possessed by itself as an atomic number. Another one is the number of electrons which are given to it by ligands it is attached with. Now I'll deal with one of the very simple example over here, and I'll give you the mathematical formula. And this is a one kind of approach only. This doesn't apply to everywhere. It's not a mandatory kind of thing. It's just like the law of octet, which works somewhere, which may not work somewhere. Take this example, everyone. This example, cobalt with hexa ammonia Cl3. Write down its oxidation state first. X plus 6 times of 0 charge on ammonia, 3 into minus 1 charge of chloride. X comes up as positive 3. So how many electrons does it contain? So we know it's a cobalt with 3 plus. So electrons are how many with it? Z minus 3, 24. And there are 6 ligands which are donating 2 electrons, that is equals to 12 electrons. So total electrons with cobalt 3 plus here are 24 plus 12 is equals to 36, which is equals to uh, helium, neon, argon, krypton. 36 is the atomic number of krypton. So that is what this rule says. This rule says that while the formation of complexes, the complexes may acquire the number of electrons from ligands, may acquire a oxidation state, and the total count becomes equal to the nearest noble gas. If you consider 3D series, it's as simple as that. Let's say this is the central atom, oblique ion, and this will come as the effective atomic number. If your central atom belongs to 3D series, 4D series, 5D series, then effective atomic number will be helium, neon, argon, krypton. Krypton is the nearest one, or 36. Now you add for 4D series, (54), that is for xenon. Then add 32, 86. Like this. Now it is not mandatory that everywhere it will be following the same rule. It may follow or it may not follow. Take this example. Okay, let me just give you the mathematical formula for this. So guys, always use this formula. Z is effective atomic number Ian is equals to Z minus oxidation state. Z is the atomic number minus oxidation state plus 2 times of the coordination number, because coordination number is the number of coordinate bond, and in every coordination bond formation Central atom has to accept two electrons, a pair of electrons. So you people are welcome to ask any kind of doubt you are facing, but you're not supposed to tease your teachers in the comment section. So I literally have blocked one person here. Chalo. Now I'll give you one of the example from iron cyanide this complex, and first of all you need to identify the oxidation state, which is x plus 6 times of minus 1 is equals to minus 3, so x comes up as positive 3. So effective atomic number will become what? Z, which is 26 for iron minus its oxidation state plus how many number of coordination number is 6 into 2. So this becomes 23 plus 12. Oh my god, 23 plus 12. This is 35. So it doesn't follow, not following Ian rule. It is not following effective atomic number rule. Let us check if it follows or not. Chromium has an atomic number of 24, and x plus 6 times of 0 is equals to 0. X also comes up as 0. 0 oxidation state is here. So effective atomic number is equals to atomic number plus, sorry, minus 0 plus 6 times of 2. So this is following. So the significance of effective atomic number is the one which follows effective atomic number are more stable compounds. What is wrong with you, creative mind? Next is, so everybody keep on liking the session. Everyone do like the session. I know that we all are enjoying the session till now. Whoever is watching and whoever is like seriously doing the preparation, whoever is properly writing the notes, whoever is trying my questions here, these people will surely get selected. And I can't guarantee for all, but yes, the one who is doing it by the heart, he will be definitely selecting. Also do one thing, this notes is absolutely like, it's very much valuable notes, and I know these notes have been made by me, and these notes can help you not in your JEE Main preparation, in your advance also. And believe me, every notes is a self-explanatory notes. It's a self-explanatory, like once you get these notes, you'll read it by your own, everything will be very much clear to you. So just download the notes from our Telegram channel and join the Telegram channel ASAP today. Link is in the description. Moving forward, we have Ian for the Bridget complexes. What is the meaning of Bridget complexes? Where single, sorry, what is it? Bridget complexes, Bridget carbonyl. So one of the example is, so guys, sometimes there is like metal bond and also be there. So this metal bond shares two electron like this. Very important part I'm telling you. If in case, if any bridged ligand is given to you, and let us say this is the ligand, we all know what is this ligand all about. This is bridged ligand. So guys, do not commit this mistake of counting two electron. Just simply need to count one electron each. One electron shared here, one electron shared here, like this. This is an important part I'm telling you. Now let's try solving some questions and then we'll move forward to the another important theory called as valence bond theory. So this is something that effective atomic number of metal ion in which of the following complexes is found to be equal to the atomic number of krypton. Krypton we all know is Kr. The atomic number is 36. So we have to tell them where can we find the krypton. Okay, Pd can never be it because see nickel, palladium, platinum. It's a 4D 4D series member, and 4D series member have nearest noble gas of xenon 54, not of the krypton. So this is incorrect. Then chromium is in oxidation state of positive 3. So let us try if it works. 24 minus 3 plus 6 times of 2, 35. Not correct. This is also not correct. Oh, not 35. 21 plus 12. $33. Another is cobalt En whole thrice Cl3. So this also has a cobalt 3 plus test. So 3 plus, and I think this will have 23 minus 27 minus 3 plus 6 times of 2. This is like 36. This is good. So this is the correct answer. C. C is the correct answer. That is how we do. So those who haven't liked the session, do like the session first. And after finishing this very important topic of effective atomic number, we have jumped to valence bond theory, VBT. So we'll see what VBT has to say. Valence bond theory says that the central atom ion, central metal ion, has an empty orbital for accommodating the electron pair coming from the ligand side, and that's why the complexes are found by the transition inner transition elements, because they have plenty of vacant orbitals to accept the electron pair coming towards them. The formation of complex involves the reaction between the Lewis acid, which is electron pair acceptor, and that is central atom, and electron pair donor is Lewis base, which is ligand, which form a coordinate covalent bond between them. The model utilizes the n-1 d ns np. So these actually are the orbitals of similar energy. Orbitals of similar energy undergo overlapping or intermixing, forming a new set of orbitals called as hybrid orbital. They will form a new set of orbital called as hybrid orbitals, and then giving a definite geometry such as octahedral, tetrahedral, square planar, like that. And the number of unpaired electron measured by the magnetic moment of the compound determines the d orbitals are used. Okay. So unpaired electrons are also a very important parameter deciding the magnetic property of a complex compound. So guys, this is something that we have to take into account, that whenever coordination number is given to you, what possible hybridization is there and what could be their geometry. So starting from 6, 6 maybe internally it can be inner orbital complex DS2sp3, or sp3d2 is the outer orbital complex where Nd is used. Here we are using N minus 1d. Here we are using Nd. So this is called as inner orbital complex. So this is called as outer orbital complex. This is called as inner orbital complex. But both of these both of these have the same geometry of octahedral. Then we have sp3 in case of coordination number 4. sp3 is the actually the geometry will be tetrahedral, and if it is dsp2, I'll let you know how do we define it. It will become square planar, and for this it's a common thing, that's a trigonal bipyramidal sp3d2. The main important hybridizations for us, the main important theory, valence bond theory for us is dealing with two type of complexes. One of them is with coordination number 4, another one is coordination number 6. So initially let us start it from the 6, and I will tell you how do I decide whether it's an inner orbital complex or outer orbital complex. I'll let you know about it. Very first, let us take this idea that both of the complexes, whether it is inner or outer, they all have this uh, similar geometry, octahedral. Both of them are having octahedral geometry. Then one of them is sp3d2, another d2sp3. Nd orbital is used, n minus 1d orbital is used. Outer orbital complex, inner orbital complex. So coordination number is 6. We are dealing with some of the molecules. Always remember, guys, whether there is a d1 configuration, d2 configuration, and a d3 configuration, they will always show d2sp3 hybridization. Whether you are using strong field ligand or you are using weak field ligand. But if the configuration is D8, D9 and D10, and this will always show sp3d2 sp3d2 hybridization, whether it is a strong field ligand or a weak field ligand, like that. Anyways, I'll come to one example first. So let me just explain you one example and you will properly relate this example with. Let's say this example is COCl6 or COH2O whole 6 Cl3 versus we have these are two complexes, okay, this and this. So guys, what happens here? Here we all know the cobalt is in positive 3 oxidation state, and the configuration of cobalt 3 plus will become argon 4s2 yani 4s0, and for I must write it like 3d and 4s like that. So it will become 3d 4s0, 3d7 4s2, so 3d6, it will become 3d6, and like this. So what happens that Cl minus, being a weak field ligand, it doesn't go for pairing, okay, it doesn't push for pairing, so doesn't pair. Doesn't pair means it will simply be remaining like this. Ek, two, three, four, five. Then we have 4s, we also have 4p and 4d here, so here is also 4p, this is 4s, this is 4p, this is 4, not 4, this is n minus 1d. See, this is forming an inner orbital complex here, this is 3d. How many electrons are there? 6. So 1, 2, 3, 4, 5 and 6. So No, 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 it's not an inner orbital, it's an outer orbital complex, by the way. Because what I need is, we need 6 empty orbitals for incoming 6 ligands. So guys, how many orbitals can participate in overlapping? 1, 2, 3, 4, 5 and 6. So these 6 orbitals will form what? 6 sp3d2 hybrid orbitals. Now you can easily identify hybridization is sp3d2. Geometry will be no doubt octahedral. Another thing that you can observe is its magnetic behavior. It will be diamagnetic. It's paramagnetic in nature because there are unpaired electrons. So many things are being. It's an outer orbital complex because inner d is not available for bonding. Now, what will happen on the contra? In the contradiction to this compound, what will happen? Same cobalt 3 plus ion is here. Configuration will be the same. Argon 3d6, 4s0, 4p and 4d. So we know that ammonia is a strong field ligand and it does pair up to the electron. Does pairing of electron means this 3d6 was earlier like this. Now this will undergo pairing and this was 4s, this was 4p and 4d. So what will happen after pairing? 1 2 3 4 5, 1 2 3 4 5 6. So guys, these are the available orbitals for bonding 1 2 3 4 5 6, and these are internal orbital. This is 3d, this is 4s, this is 4p. So now these will undergo producing 6 d2sp3 hybrid orbitals. So d2sp3 means they are involved with internal d. That is why it is called as inner orbital complex. This is called as outer orbital complex. Getting me? That is the difference between them. This is there is no unpaired electron. This is diamagnetic. This is paramagnetic. This is also called as low spin complex. This is called as high spin complex because high spin is because of the unpaired electron which cause the spin. Spin is equals to number of unpaired electron into half. That simple. Now you solve this question that was asked in 2019, JEE Main 2019. Try it. The question is pretty simple. We got to identify that ion which has no impact of strong field and weak field. So I can simply say that first of all, find out their configuration. That is highly important to us. Nickel 2 plus, I will simply write 3d8 4s2, so it will become 3d8. Iron will become 3d6. Chromium will become 3d4. Manganese will become 3d5. We all know that d8 is the configuration that will always give you sp3 d2 configuration irrespective of whether you are using strong field or weak field. The correct answer is A. How easily I made this question. How easily did I do it? And I want you people to do the same thing. Become comfortable in this. Now try another question. The difference of the spin only magnetic moment values of COH2 whole 6 Cl2 and CrH2 whole 6 Cl3. Difference between the magnetic moment of this and this. So spin only magnetic moment. I will ask for I'll try to calculate it for the first one, which is CO 3 plus, and that also with weak field ligand. This is Cr 3 plus with weak field ligand. This is 3D 6 4s0 4p0. D6 electrons will be filled in D subshells like this: 1, 2, 3, 4, 5, 6. Number of unpaired electrons are how many? 4. Mu will come up as root of 4 into 4 plus 2 Bohr magneton. So that is gives you 4 into 24 Bohr magneton. Okay, we all know about this formula. If not, then learn it right now only. Spin only magnetic moment is equals to mu. I'll write it over here. We call it spin only magnetic moment mu is equals to root of number of unpaired electron n into n plus 2. The unit is Bohr magneton. We study this formula several times in so many chapters, such as like in Bohr, in atomic structure, we also have covered this formula. Just learn this formula and apply it. Now I'll count it for this Cr3 plus has 3D 3 4s0 4p0. I think the number of unpaired electron over here will also be 1, 2, 3. How come is here 3 or 4? What is the answer given? No answer is given. So you can calculate the mu. Number of unpaired electron are coming up as 3. Chromium 3R. Chromium has 24. 3d4 4s2. 4s2 is gone. 3d3. So this will become 3 into root of 3 into 3 plus 2. Root 15. So guys, what we have to find out is the nearest number. So nearest number of difference will be root 24 minus root 15. This is nearly 4. This is nearly 5 minus 4 is equals to 1. 1 is the correct answer. So now we have come to the coordination number 4. We'll take this idea of coordination number 4 also as VBT. We'll wind up this session. We'll then we'll continue from the upcoming topic after a short break. Okay. First, let us finish this part also. Hybridization. So sp3 versus dsp2, these are two different type of possibilities may happen, and it all depends upon the nature of strength of weak field versus strong field. Although even I do not have learned the entire sequence of spectrochemical series, but I have this idea and I can show you how can you find strong field ligand versus weak field ligand, because this is something that is very important to us, where we have to pair up the electron, where we do not have to pair up. Strong field ligand are basically carbon donor more than nitrogen donor. So guys, these are the strong field ligand, just like carbon monoxide or carbonyl, cyanide, ammonia, ethylenediamine, etc. What about the weak field ligand? Weak field ligand actually could be oxygen donor and then X donor. This X donor is actually halide. So guys, this order is like oxalate ion, water, hydroxide ion, Cl minus, Br minus, I minus. So just remember this, take this idea in your mind. Wherever oxygen and halogen donors are given, they are considered as weak field ligand. Wherever carbon and nitrogen donors are given, they are considered as strong field ligand. So this is how we can take this idea and we can continue from valence bond theory. Later on, when we'll come to the crystal field theory, there we explain the exact data, the exact explanation behind the spectrochemical series. Until then, just keep enjoying. Coordination 4 has some very important critical compounds that we have to discuss. I'll start with very first and very important one. Let us take this compound as nickel tetrachloride. Nickel tetrachloride. So what you'll see, nickel no doubt is present in positive 2 oxidation state. The configuration will become 3d8 4s2. So 3d8 4s0 4p0. We all know how does d8 look like. Like this. So how many number of unpaired electron can you see? 2. How many number of vacant orbitals are there? Because we know that there are 4 chloride ions are approaching to donate their electron pair. So these 4 orbitals will participate in hybridization. They undergo intermixing, they form 4 sp3 hybridized orbitals. So guys, what conclusion did we get from here? How did we get this configuration? Okay, because Cl minus being weak field ligand does no pairing. So there do not occurs the external pairing of the electrons for central atom. Simply keeps it like this. Next things comes, what will be the impact of this molecule? This molecule has hybridization sp3. This molecule has a geometry tetrahedral. This molecule has a, what else can we see? Magnetic behavior. Since it has unpaired electron, it is considered as diamagnetic. Sorry, paramagnetic. Anything with its number of electron is called paramagnetic. Since outer orbitals are participating, so only outer orbital complex. No inner D is participating. Since there are 2 unpaired electron, it is called as high spin complex, where there will be a complete no unpaired electron will be there. Those becomes low spin complex. Since there is a unpaired electron, this is called as high spin. Now I'll take you to another example. Nickel has 3 very important examples that we need to study. One of them is with weak field ligand. The another comes with strong field ligand and the similar kind of molecule, NiCN whole 4. Tetracyanide with 2 minus charge here. We all know Oxidation state is positive 2. So nickel with positive 2 oxidation state comes up as 3D8, 4S0, 4P0, 4D0. So D8 configuration somehow look like this. 1, 2, 3, 4, 5, 6, 7, 8. See, but Cn minus being strong field ligand does pairing. So what will happen, guys? This pairing, this pairs up with this, finally becomes somehow like this. This is vacant like this. This is your 3D. This is 4S. This is 4P. 3D, 4S, 4P. So the hybridization will become this, this, and this, because we need 4 vacant orbital to accommodate the electron pair coming from 4 cyanide ion. So this undergoes hybridization and produces 4 DsP2 hybridized orbitals. So now I'll write the every description here. Hybridization, DsP2, shape oblique geometry. What will be the geometry of this molecule? The geometry will become square planar. Earlier it was tetrahedral, now it has become square planar. Number of unpaired electrons are how many? 0, because all went paired up. So that is why magnetic moment will become 0, and this species will become what? Diamagnetic. Its magnetic behavior is what? Diamagnetic nature. Earlier it was paramagnetic because it had number of unpaired electron. Talking about the inner or outer, since inner d orbital is used, it is called as inner orbital complex. Since all the electrons went for pairing, no unpaired electron is there, it is called as low spin complex. Check it out. These are the properties we got to find out using their hybridization, using the electronic configuration, knowing the nature. Yes, halwa recipe for NEET, good. Good, MacG, good. No idea on what construct did you say it, but good. Keep it up. Make it large. NEET people have to make it large. We have another third one. We also have another one. What was that given? Video cannot, that's a different thing. Third example is also the similar one, but a different one also. Although it's similar, but it is different also. Similar but different. Third one. The third one is nickel tetracarbonyl, which is another important example. What happens in the case of nickel tetracarbonyl? Nickel itself is present in the oxidation state of 0 because carbonyl has no charge. The configuration becomes 3D8, 4S2, 4P0, 4D0. Everything was chill until the strong field ligand came into the game. How many number of electrons are here? 8. 1, 2, 3, 4, 5, 6, 7, and 8. 4s, how many electrons are there? 2. 4p, and then 4d. So we have, what do we have with us? We have carbonyl, CO, being strong field ligand does pairing. It does pairing of electrons. So once the electrons are paired up, what will happen? This goes here like this. Configuration now becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even the 4s is now empty, 4p is now empty, and so does the 4d. This is 4s, 4p, 4d. How many electrons are approaching? How many ligands are approaching? 4. So we require 4 empty orbitals to accommodate 8 electrons. These will go under hybridization, forming 4 sp3 hybridized orbitals. Now we have 4 sp3 hybridized orbitals. So how are we supposed to write the all properties? Very simple, as we have discussed it earlier. So hybridization will become sp3. Geometry of the molecule will become tetrahedral. Number of unpaired electron 0. Complex is still outer orbital complex because all the d orbitals are filled here. Complex is outer orbital complex. Okay, magnetic behavior. What do you comment about the magnetic behavior? It's a diamagnetic because all the electrons are paired up. No unpaired electron is there. So diamagnetic in nature. Next is what next? I think that's it. So now outer orbital complex. Outer orbital complex. What else do we have? Low spin complex. There are some more important points that we have to cover here. We always need to take these points into account, that whenever we have 4D or 5D series member with us as central atom. In the case of 4D and 5D elements as the central atom, all kind of ligand, even a weak field ligand, behave as a strong field ligand, and they all pair up. And that's why in such kind of coordination number equals to 4, they will form dsp2 rather than forming sp3, and thus they become, that is why pd2 plus will always give you 4d8 like this. This will give you dsp2 hybridization, and the geometry will become square planar. So all the complexes of pt2 plus will always be dsp2 hybridized rather than sp3. Learn down, this is a very important part I'm explaining. Now we'll solve some question, we'll take a break, and we'll restart it from crystal field theory. Now take this. The question is, in which of the following pair both the complexes have same geometry? Both the complexes with same geometry. Same geometry. Okay, 6 will have the same geometry, no? 6, because octahedral, whether it is inner field, outer field, 6 will be the octahedral in nature. JEE Main 2018 question is asked. Correct combination. As I told you, this is very important. This square planar, incorrect. CN4 2 minus tetrahedral, incorrect. Paramagnetic, correct. NiCO4 tetrahedral, correct. C is correct, I guess. See, I explained you recently. Which of the following will have a square planar geometry? I told you PT2 plus will always have the square planar. D is the correct answer. Even without seeing the option, even without undergoing the options, I can solve this. Now it is up to you people. You need to solve the rest of the question as homework. These are the limitations of VBT, that there were a lot of exceptions, assumptions were there. There was no quantitative interpretation magnetic data because we didn't know about the strong field and weak field ligands. Doesn't give you the color exhibited by coordination compound. doesn't interfere with the dynamic, thermodynamic, and kinetic stabilities of complexes, why the complex of copper is stable whereas it is an outer orbital complex. There were so many things that was not explained in the case of VBT, and we will discuss these points under very important theory called as crystal field theory. Rest you solve all these questions. These are for you. This is where we'll start it from now. So let me just take you to first to this limitations. Let us take a break from here. It's been continuously 2.5 hour we spent. I think we all require a break, a short break from here. So guys, we'll connect shortly. Wait, everyone. I'm trying to resolve this issue. सेकंड एक इशू था मैं अभी जस्ट Hi guys, so let us begin it from here. We till now have completed valence bond theory, and our upcoming topic is crystal field theory, which is very important topic as far as concern of this entire chapter. The mostly asked topic, heavy weightage chapter, heavy weightage topic, crystal field theory. Okay, so let me start crystal field theory. Hopefully, you all have joined back. That was a healthy break we had. CFT is our new topic. CFT, crystal field theory. So, guys, what does crystal field theory has to say? Because of the unsymmetric field of the ligand, degeneracy of d orbital is lost and splitting of d orbital occurs. So, we all know that d orbitals are different in shape and especially different in their orientations. For an example, this is x-axis, this is y-axis. This orbital dx square, sorry, this is dxy. Dyz, this is dxz. So these axes are x and y and z, and let's say x and z. The another remaining two orbitals, these are called as non-axial orbital. The remaining two lie along the axis like this. This is dx square y square along x and y axis, and then comes another one called as dz square. This is your z axis. This is dz square. So now what happens, since we all know that all the d orbitals have different orientations of their electron density, whenever the ligand will approach, some of these orbitals will be in the direct facing the ligand, and ligands might be carrying a negative charge. Orbitals also have electrons in them, and they are also what we can say possessing the same charge. Okay, allow me a second, everyone. Hello? Hello. So now what will happen? There are two things that we have to study. One of them for the octahedral complexes, and another one will be for tetrahedral complexes. So what happens in the case of octahedral complex? This is an octahedral complex. Initially, the metal atom has degenerated orbitals. All the atomic orbitals are at the same energy level. Then all the ligands try approaching towards the central atom, due to which the average energy of all these orbital increases. How much does it increase? Increases a bit. That is what we call as the symmetrical spherical crystal field. Okay, we call it symmetrical spherical crystal field. This is called as metal free atom. Right after that, what happens? Orbitals will be getting closer to the ligands. Some of them will be highly closer to them, some of them will be getting farther from them. In the case of octahedral, okay, let me just tell you guys, in the case of octahedral, 6 ligands approach from plus x, minus x, plus y, minus y, plus z, minus z. This is how the ligands approach from all the directions, forming an octahedron. You guys can check it out. This is central atom at the center of this. Metal N plus. Central atom is at the center of this. So what will happen here? The degenerated orbitals lose their degeneracy. Some of them acquire higher energy, some of them acquire lesser energy. The less energy orbitals are the one which are in farther from the incoming approaching orbitals, approaching ligand. This is dxy, yz, and zx. We call them T2G, triply degenerated orbital. Similarly, there are two orbitals dz square, dx square, which feel equal repulsion, and their energy gets increases. We call them equally degenerated orbital. The difference of the energy between these two is called as delta O, and delta O is called as crystal field splitting energy for an octahedral complex. Crystal field splitting energy for an octahedral complex. So now, using this, we can find out the formula of CFSE, called as crystal field stabilization energy. crystal field stabilization energy, CFSE. Crystal field stabilization energy is calculated by this, that number of electrons which are present in T2G multiplied by T2G electrons are basically in the negative energy over here, and this is multiplied by negative of 2 by 5 delta O plus number of electrons in EG multiplied by their energy increases by 3 by 5 times of delta O in positive value, plus however the number of pairing occurring NP. This NP is very particular number. I'm telling you, this NP is very particular number. This NP will be used in the case where weak field ligand or strong field ligand create a difference in the number of pairing. Might not be understandable as of now, but allow me some time. I'll explain this point when a question will come on this particular concept. Okay, give me a second. Hello, how are you? Let us continue from here. This is the formula that we have to use in order to find out the crystal field stabilization energy for. This is not splitting energy, this is stabilization energy. Somewhere it is written in the terms of splitting energy also, but both of the values or both of the meanings are the same. We got to follow, we got to find out the crystal field stabilization energy for an octahedral complex like this using this formula. And I'll give you one example to explain this. But first, let us move forward. So there could be two possibilities. One of them could be a weak field ligand present, or another could be the strong field ligand. So a weak field ligand does no pairing, and a strong field ligand does pairing. Upon basis of that, only different electronic configuration will be received, different electronic basically distribution will happen. And this is the spectrochemical series, which is an experimentally driven data that I was about to explain you, that I was telling you while I was explaining you valence bond theory, that as of now you learn the entire sequence in my way. Just like carbon donors are the strong, carbon nitrogen donor are strong field ligand, oxygen and halogen donor are the weak field ligand, carbon and nitrogen donors are cyanide, carbonyl, this is SCN, CN, what is this here? Okay, this is CO, CN, EN, NH3. This is the correct order. I minus, Br minus, Cl minus, F minus. Let us try one question that was asked back in 24 this year only. Okay. JEE Main 2024 asked this simple question: what is the order of field strength? Now we direct answer is given here. Okay, my bad. But we all know carbon and nitrogen donors are the stronger one. So this is incorrect. This order is actually incorrect. This comes with fluorine followed by chlorine, bromine, iodine. This is how it follows the strength of ligand. Coming to this part, ammonia, this is incorrect because cyanide is more stronger. Cyanide is a stronger ligand than ammonia. Then bromide, fluoride, hydro, this is correct. And Cl, this is also incorrect. This part is incorrect. Halogen are lesser field, have lesser field strength than oxygen donor one. So that's why the correct answer is C. This kind of question directly question came from JEE 2024. So another question is here in back asked in 2019. The question says that the complete removal of both axial, if we are removing the completely the z axis from the octahedral complex, which leads in the formation of splitting pattern in which of the following way? So guys, I'll let you know about it. And this is also very good question. This is nothing but the configuration asked for the square planar. We all know that if we remove z axis from the octahedral complex, it will become what? It will become square planar. So square planar actually follows this way, that x square y square will be highest, then xy, then dz square, and then comes your xz yz. I think this is the A is the correct answer. Next question from JEE Main 2019 till what we have discussed right now. The metal d orbital that are directly facing the ligands in this are the metal d orbital that are directly facing. So directly facing in an octahedral complex are what? In an octahedral complexes, ligands are coming from plus x, plus y, minus y, plus z, minus z. So you can assume that from the center of the walls, center of the faces of the cubes, these ligands are approaching, and at the center of this cube, the situated part is your none other than cobalt 3 plus ion, central atom. Correct answer, dx square y square dz square. Among the following, which of them is having higher crystal field stabilization energy? Higher crystal field stabilization energy will be for stronger field ligands and higher oxidation state possessing one. So you can check it out. All of them are having positive 3 oxidation state. So there is only one thing that can decide the factor, that is the field strength, and field strength is maximum for cyanide. A is the correct answer. How easy is it? The complex that has the highest crystal field stabilization energy. Which one has the highest splitting energy? Okay, highest splitting energy will be, okay, first of all of them are, now this is tetrahedral. So tetrahedral has lesser CFSE. This is octahedral, this is octahedral, this is octahedral. Then octahedral with the highest number of strong field ligand. I think cyanide is the perfect one. D is the correct answer. See how easy these questions have been asked previously. Another question from JEE Main 2019. JEE Main 2019 asked us a question that out of these three complexes are there, and these absorb the light in visible region. Correct order of the wavelength absorbed by them is what? So guys, we all know that delta, or we can say that crystal field stabilization energy is directly proportional to, or we can also say that for different complexes, delta O will also be different. So whatever the difference between the energies there is directly proportional to 1 by lambda. Okay, because this is nothing but the hc by lambda. The energy is hc by lambda. So what happens in the case of hc by lambda delta O? We all know that maximum separation will be seen in the case of, or maximum energy gap will be seen in the case of stronger field ligand, which is ammonia, I guess, then followed by this one, not this one. Water is stronger ligand than this. So let us say that delta O, or crystal field crystal field splitting energy, forgot the term. Crystal field splitting energy, CFSE, is actually greater for third, followed by second, followed by first. So how would it, this is the hc by lambda. So lambda will follow the order of first, second and third. Where is the first, second and third? Can you see? Arey yaar, this is same thing yaar. First, second, third in decreasing order. So first, second and third, I think this is the correct answer, D. So that's how we do. Which of the following configurations of metal cation octahedral complex can't be classified high spin low spin? I told you D6, D7, D8 and D1, D2, D3. So where can you see D3 and D8? A. Perfect answer. हाँ. So guys, earlier we were discussing one example and I told you that I will explain this part of pairing energy by that time only when some question comes, and this is the perfect question that we can explain. So try focusing on this question. Low spin complex of D6 cation in an octahedral field has the following energy: delta O is an octahedral field, P is the pairing energy. What should be the correct value of CFSE? CFSE is called as crystal field stabilization energy. So let us see how can we find out. Following energy. Okay, so see, first of very all, this is D6 configuration. So with the weak field ligand, so weak field ligand does what? There is a low gap between these two energy levels: 1, 2, 3, 4, 5, 6. How come we filled these before this? Because there is a low gap between these due to weak field ligand. Strong field ligand has higher gap. You got to pair these electron all, then only you can fill this if it is fully filled. So configuration is pretty much clear to us. Now if we apply the formula, or let's say if you also, okay, no, we have done it incorrectly. In the case of weak field ligand, if you do the same thing, if you do the same thing in the case of D6 configuration using strong field ligand, okay, I forgot it. It has been asked that low spin complex has to form. Low spin means number of unpaired electrons should be as lesser as possible. So I'll make this as this. All 6 electron will go here. 1, 2, 3, 4, 5, 6. No electron over here. Now you will understand the concept of pairing energy. So if it was a weak field ligand, then one pairing was automatically happened here. There was no other option than to pair this electron. But in the case of strong field, two extra pairing are occurring. Two extra pairings are occurring. Two extra pairings are happening. So now we can apply the formula of crystal field stabilization energy of this system for strong field ligand will be, how many electrons can you see here? 6. So 6 electron into minus 2 by 5 delta O plus 0 electrons multiplied by 3 by 5 delta O plus how many extra pairing? Okay, one pair was already there, 3 pairs are here. You need to think what extra pair is there. So 2p is the correct answer. So minus 12 by 5 delta O plus 2p. This is the correct answer. B. Getting me? Yes. Now we'll come to tetrahedral complex. Once we have finished the octahedral complex, now is the term we need to study about tetrahedral complex. Tetrahedral complex is pretty easy to explain. What is happening here? That it's a tetrahedron, by the way. So tetrahedron, 4 ligands are approaching in such a direction. 4 ligands are approaching in such a direction that a tetrahedron is formed. You can imagine this thing as, you can imagine this whole system as, uh, let us suppose this is a corner. This corner is connected with one face, second face, and third face. One corner with 3 faces forming a tetrahedron, and towards the center of it, the 4 ligands are approaching toward that corner, face center, face center, face center. What actually happens? 3 of the orbitals which are non-planar, which are non-axial, dxy, dz, dxz, they acquire more energy now. And the axial one, dx square, y square, and dz square get the lesser energy now. So the opposite thing happens here. 3 orbital dxy, yz, and zx goes at higher energy with 2.2 by 5 delta O, and minus 3 by 5 delta T comes with the individual orbitals over here. So the mathematically the formula becomes exactly the same as it was earlier. So crystal field stabilization energy in the tetrahedral complex will be what? Number of electrons in, first of all we got to take it for the down one, which are E electron, I guess. We don't call them EG, we simply call them E, because this is a different concept of symmetry and non-symmetry. We call it G-rayed and non-G-rayed, un-G-rayed. We simply will say E. So number of electrons present in E multiplied by minus 3 by 5 delta T plus number of electrons which are present in T2. We do not say T2G, they are not G-rayed, they are un-G-rayed because of the unavailability of symmetry. This is positive of 2 by 5 delta T plus same number of pairing into P, pairing energy. And this P again, it's a very subjective term, it depends upon the configuration as a difference between strong field ligand and weak field ligand. Sorry. So what is the relationship between delta T versus delta O? So guys always know that this 6 ligands were approaching with more energy, that is why delta O is greater than delta T. And how much? Delta O is actually equals to 9 by 4 times of delta T. Remember this formula. One question back asked in JEE Main 2020, the values of crystal field stabilization energy for a high spin D6 metal. We have already completed it or not? No, we haven't. So D6 has to be applied for both octahedral and tetrahedral. So CFSC for octahedral, CFSC for tetrahedral. Configuration is pretty much known to us, D6. Okay, this is actually D6. So here it will be for octahedral, this is the separation. And what is it, by the way? High spin. So 1, 2, 3, 4, 5 and 6. This is a high spin. And what about the tetrahedral? Tetrahedral will be having like this. So 1, 2, 3, 4, 5, 6. This is how the electronic configuration works. I can name these orbitals as this is your T2G, this is EG, this is simply E, this is simply T2. Now try solving this and find out the final answer. Crystal field stabilization energy. Crystal field stabilization energy. 6 multiplied by negative of 2 by 5 delta O, 2 multiplied by positive का 3 by 5 delta O. This will become what? Negative 12 by 5, positive का 6 by 5 delta O, 0 point, sorry, it is 1.2, I guess. What is it? 6 by 5. So yeah, none of this is matching here. How come? Minus 12 by 5 and positive 6 by 5. No idea, dude. Minus 1.2 delta. Anyways, this energy will always be coming in negative and maximum it can be 0. This energy will definitely be coming in negative only. That is not a problem. For tetrahedral, this is how many? 3 into negative 3 by 5 delta T plus 3 into positive 2 by 5 delta T minus 9 by 5 delta T plus 6 by 5 delta T. So this will become what? 9 minus 6 is 3. 3 by 5 is 0.6 minus 0.6 delta O. So this is the correct answer actually. Okay, I think I have made some mistakes here. It is saying that high spin is fine and d6 in octal is, I don't know what, where, maybe the options are incorrect here. Minus 1.2 delta O, then comes this. So anyways guys, this was our crystal field, sorry, this was your crystal field theory, CFT. Very important theory as far as the concern of coordination compound, very frequently asked back in few years, especially in JEE Mains and Advanced. Now colors in coordination compound, and major reason behind the colors in coordination compound is called as due to DD transition, due to DD transition. The color in complexes arise due to DD transition. How are we going to learn this DD transition? It's very simple. Wherever there's an unpaired electron, let's say this is a part of octahedral complex, since unpaired electron can acquire some energy, can absorb the energy h nu, and then gets jump, then come back, and whatever the remaining light is there visible to us, and that is called as complementary part of that light. So what is the meaning of this thing? Let me explain you here. Take this example, everyone. This is a circle. This circle is actually a pizza of 6 slices. So just 6 slices I'll make. Simply write V, B, G, Y, O, R. I know that among this color wheel there could be lots of colors possibly, but I would go for only those color for which we can find out the correct answers, and easily we can learn this thing. So guys, there are two things. One of them is absorbed. So let's say some particular complex absorbs this color. This is the absorbed color. The color which is right opposite to it will be the visible color. And we can say that orange, the one which is absorbed, is the blue. So orange is the complementary color. Complementary means the one which is visible. Complementary color of blue. That's how we do. Getting me? Orange is the complementary color of blue. Next, identify the complex which is expected to be colored. You got to find out the number of unpaired electron. Wherever the number of unpaired electron is there, it will go for D transition. It will create a colors in the complex. So this is your titanium, cadmium, vanadium, scandium. Now find out the number of unpaired electron. This is your argon, 4s0, 3d0. This is argon, not argon, this is cadmium, krypton, 5s0, 6d8. No yaar, zinc, cadmium, mercury. So D10 will be here, D10. So again 0 unpaired electron, scandium, titanium, vanadium. This will be argon, 4s0, scandium, vanadium, 3, 3d3. So this will become 3d, after 2, 3d2. So 2 unpaired electrons are here. No, just 3d, 3d2. And the last scandium, argon, 4s0, 3d0. So which one of them is having the unpaired electron? Only this. 2 unpaired electrons. ये सब बाकी रेस्ट zero unpaired electron, zero unpaired electrons, zero unpaired electrons. Correct answer is actually C. Next question is here, and I would expect you people to please solve these questions as homework. I have plenty of other topics to finish today. So now I'll come to the limitations of crystal field theory that we came across. The number one drawback of this theory is it assumes ligands as point charge. So if the ligands are point charge, how come the charged one halide ions are placed as low field or ligands, and the neutral ones are considered as strong field ligands such as carbonyl, ammonia, etc. This theory doesn't consider the covalent character. This theory consider ionic nature, ionic interaction between the central atom and ligand. Another thing, we have stability of complexes. Stability of complexes is an important topic and explained under under certain conditions, such as number one, if oxidation state varies, the higher oxidation state will be having higher stability, because if something is having higher oxidation state, something will be, some cation, some central atom will be having higher number of vacant orbitals available for the incoming ligands. Higher is the Z effective, higher is the central atom. So always remember that 3D, 4D and 5D, this is the order of Z effective. So if some nickel complex is there, platinum complex is there, or palladium complex is there, platinum will be the winner. Charge density and strength of ligand. So strength of ligand is directly, stability is directly proportional to the strength of ligand. So strong field ligand will make more stable complex than the weak field ligand, like this. Now JEE Main 2020, one question came in JEE Main 2020. Which of the following is highest stability constant? Like which of the following is more stable? So guys, I need to explain you this part, which is highly important. Let me just cross check one part. Mm, there is something I'll explain you, which is not in our syllabus, but I would expect you people to directly learn it. And everywhere you will come across this part, that usually this octahedral complexes are more stable than tetrahedral. But what about the square planar one? So guys, this is something we have to learn, that stability of complex is first of variole directly proportional to the what is the type of crystal we are having, tetrahedral, octahedral, or square planar. So it is directly proportional to the delta, crystal field splitting. And the order of splitting is delta O. Square planar is higher than delta O, is higher than delta T. And I can explain how does it vary also. The delta SP is nearly 1.3 to 1.7 times of delta O. Delta O is 9 by 4 times of delta T. So this is how. So correct answer should be, I think this is the correct answer. So this is the square planar complex. Allow me a minute, I'm coming back with water. So guys, I'm back. So these one shots, especially for 6 7 hours or 5 or 4 hours, we usually take. These are very exhausting, especially for a person who just have recovered from the big viral fever. So I sometimes find myself difficult to perform continuously for 4 and 5 hours, and that's why I went to take some drinks and a drinks break. So this is something that you'll do by your own. Now I'll take you to another important topic called as organometallic compound. Very simple topic. Organometallic compounds are those compounds in which there is a direct metal carbon bond, and this metal carbon bond in the organometallic compound could be of metal carbonyls, cyanides, everything. But take this thing in account that there could be three type of metal and carbon bonds. One of them is called as sigma bonded complex, another is called as pi bonded complex, another is called as sigma plus pi. Sigma bonded complex means where the direct carbon and direct sigma bond is there. Take this example like C2H5 whole 4PB. We call it tetraethyl lead. So what you can see that lead is directly bonded with C2H5, 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 C2H5 like this. So this is tetraethyl lead. Pi complexes are the one in which there is one pi electron density which will be donated to the central atom, Just take an example of Z salt. Z salt has an alkene which is ethene, and ethene is donating this electron pair here to the platinum. Similarly, ferrocene is one compound. This bisbenzene chromium is another important compound. Then we have metal carbonyls, and metal carbonyls are said to have sigma plus pi bonded complexes. This sigma plus pi type of bonding is also called as synergic bonding. This is also called as synergic bonding. So what happens in case of synergic bonding? Metal is once accepting the electron pair from the bonding pair of the carbon. This lone pair will be donated over here. The very next moment what happens, carbon has these anti-bonding molecular orbital where the electron pair so called these present inside the metal will be donated back to the carbonyl, due to which this bond strengthens because it's a kind of double bond is happening. Double bonding as in one sigma bonding is happening directly to the vacant orbital of metal from the carbonyls, this orbital, bonding orbital. Then another bonding is happening from metal to the anti-bonding orbitals of pi star. This bonding is called as synergic bonding. Because of this synergic bonding, this actually bond length decreases, bond strength increases, but carbon bond length also increases. Carbon bond energy, carbon oxygen energy, actually bond energy decreases. Let me just take you through some examples and then we'll explain what we just have studied. One of them is called as pi bonding is not involved in ferrocene, diabenzene chromium, Z salt, Grignard reagent. So Grignard doesn't have any pi bond. Grignard has a RMGX. So this is called as a sigma complex. Which of the following organometallic compound is both sigma and pi? Wherever there is a carbonyl involved, it has both sigma and pi. Which is not true for metal carbonyl? Which of the following is not true for metal carbonyl? That oxidation state of central atom is neutral, correct? Because carbonyl has zero charge on it. D pi, P pi back bonding occurs from metal to carbonyl. Wait, no, it is D pi, P pi star. This is incorrect. This is correct. See, D pi, P pi star, because pi star anti-bonding molecular orbital of carbon monoxide accepts the electron pair from metal as a pi bond, formation. Number of complexes which will exhibit synergic bonding. Wherever you can find carbonyl, all will do. 3 is the correct answer. Very simple question. Try this question by your own homework. Then we have the last thing called as isomerism. the last topic of this day, and we'll cover isomerism. We'll cover isomerism soon. Okay. Okay, try reading these things out and then I'll give you the perfect explanation on this. Yes. Now let's continue. Sir, please take organic chemistry also. First of all, thank you, Anant Raj, for sharing your feedback. Number two, this was the last chapter of inorganic chemistry. The next chapter, which I'll be taking on this channel, will be from organic chemistry only. Allow me a month or a couple of months from here, and believe me, we'll finishing the entire organic chemistry from here. Or I think I don't remember exactly, but let me check it whether I have taken some GOC concepts earlier or not. If not, then I'll start it from GOC, and when we'll go accordingly. GOC, hydrocarbon, alkyl halide, aryl halide, aldehyde ketone. We'll finish whole chapter. Okay. Now the remaining part of this chapter is isomerism. Isomerism is a property of a compound due to which it may exist, or different compounds with same molecular formula have different physical chemical properties. This property is called as isomerism, and these compounds individually are called as isomers. Number one is structural, another is called as stereo. Structural could be ionization, hydration, coordination, linkage, ligand, and coordination position. I'll finish all of them in just one go. So structural isomerism, just read out the definition. Yeah. Structural isomerism is due to the difference in the types of chemical linkages and distribution of the ligands within and outside the coordination sphere. Okay. What was that? Linkages. Anyways. So one is called as ionization. Very simple, guys. Very simple. See, when you ionize this compound, this will give you what? One bromide ion only and this complex ion. If you ionize this compound, it will give you one sulfate ion. But the formula overall is same. Only the difference is Br minus over here is working as a counter sphere or ionization sphere, and sulfate is working as a ligand. Here sulfate is outside and Br minus is working as the ionization sphere. This is the only difference. Next is hydration. If there is a difference of number of water molecule inside and outside of the coordination sphere, then these kind of isomerism is called as hydration isomerism. Take this example. Here are two molecules outside. Here is only one molecule outside. Here is zero molecule outside. All molecules are inside. All of them are having different colors. So this is the difference of hydration isomers, or we also call them solvate isomerism, where the number of solvent molecules differ inside and outside. comes the coordination. Very simple. Coordination isomerism occurs only in those complexes where positive charge and negative charge species both are complexes. Means cation and anion both are complexes. Just replace or just exchange their central atom and you will be getting your final answer. Like central atom is exchanged, chromium comes here, cobalt comes here. Linkage isomerism is defined only for those complexes where ambidentate ligands are used, where one of them is making like cyanide is making bond with carbon, isocyanide will be making for the nitrogen. These two complexes will be individually termed as linkage isomerism. Nitro isonitro, cyanide isocyanide. Ligand isomerism is very rare, not even in CRT it is mentioned. Ligand isomerism means whenever ligand itself has an isomerism in the case of chain or position within its configuration, within its chain. Like this is a compound, it is called as 1,3-diaminopropane. This is the compound 1,2-diaminopropane. This is symbolized as TN, this is symbolized as PN. There is a difference, there is a what we can say the difference in the structures of the ligand itself, then they are considered as the ligand isomerism. Final is coordination position. This only happens in the case of bridged complexes where the either side of the bridge will be having different groups. So take this example here, ammonia, 4 ammonia are there, 2 this. Here 3 are taken. So these two are actually the coordination position isomers. Try solving some questions. A question that was asked back in JEE Main 2021, exactly 3 years back. Cobalt, okay, we all know that this kind of thing will be definitely giving coordination isomerism, but also because of this cyanide they will give you linkage isomerism also. Talking about this molecule, the beauty of this molecule is this is having a nitro group, and nitro can be nitro isonitro also. So this will be showing you linkage. And now coming to the third one, CrH2O, solvate isomerism, because it is having water. Water may differ inside and outside of the complex. Am I right? So the correct answer is A is matching with 4 and first also. Okay, 3 and 1. B is actually 1 and C is actually second. I think this is correct. A is correct, I guess. A was correct. The last and final topic, that is stereoisomerism. So I won't take too much of your time. I have made the notes very perfect, nearly perfect. I'll share these notes. You please read it out. Geometrical isomerism is basically the spatial arrangement will be different around the particular central metal atom. You must know that none of the tetrahedral complexes show you this kind of geometrical isomerism. Only octahedral and square planar can show you the geometrical isomerism, because all the positions in tetrahedral species are identical, and that's why we cannot go through geometrical isomerism in tetrahedral complexes. Optical, we talk about optically, only a square planar can never have optical activity, because square planar has a symmetry, a plane of symmetry in it. So these are some set of numbers which are given here. How many number of GI and enantiomers have been shown by different type of molecules. Just have a read it and try finishing these all. Try this question. Which of the following species is not expected to exhibit optical? So optical isomerism will not be shown by which of the given? Ma3b3, because this shows only FAC and MER, geometrical isomerism, no optical isomerism. Simple as that. Try this question, JEE Main 2020. So the question is, we have been given with trans COEN hold CN twice and Cl2. Guys, allow me a sec. You try it by your own funds. So this is trans COEN twice. So we can write down this complex. CO3 plus is here, and there are two Cl minus ion. And if once it is trans, so we'll make the structure like this. This is, let's say, En. This is how the En connects. Okay, like this. So our question is, what is true about this given compound? Number one option, both A and B are optically active. Okay, this is trans cannot be optically active because its mirror image will be the identical. Its image will be what we can say superimposable. So it will give you a superimposable mirror image. That is why both cannot be optically active. A can be optically active. B, this is also incorrect. Both A, no. B can be optically active, which is cis, yes, and A cannot be optically active. So guys, just try apply your own knowledge. Take this thing as a homework, and now we'll connect in our next session. That is it for the day. Hopefully you all have enjoyed. Try downloading these notes. Try to do the maximum out of it and make the short notes out of it. Practice PYQs these days, because as we all know, we are getting our exams very closer by. So no need to make the complete notes and writing so many and trying so many easy questions from the resources. No, just try PYQs, try solved questions out of it. That will be enough for your JEE exam. Bye bye. Take care. See you soon.